So hello everyone, a very warm welcome to you all to today's PV Tech webinar in association with TrinaTracker. My name is Ben Willis. I'm the acting editor-in-chief at Solar Media, which publishes PV Tech alongside our other industry-leading news channels such as Energy Storage News and Solar Power Portal. Almost as astonishing as the rate of deployment solar power has enjoyed worldwide over the last decade is the extent to which trackers have become such an integral piece of hardware. It seems like not all that long ago that projects incorporating tracking technology, which positions solar panels where they will receive the maximum amount of direct sunlight throughout the day, were the outliers rather than the norm. But as solar has expanded into new geographies where the optimal conditions for solar generation, namely strong and consistent sunshine, are not readily found, so tracker technology has come into its own, enabling the transformation of marginal projects into entirely profitable ones. According to the latest figures from America's Lawrence Berkeley National Laboratory, over 90% of new utility-scale projects in the US incorporated single-axis tracking technology. And the picture for other parts of the world is much the same. And as the technology evolves, trackers are becoming much more than simply a mounting system. By incorporating sophisticated controls and an array of intelligent software systems, trackers now offer a multitude of capabilities, such as remote monitoring, analytics, and the ability to respond to developing weather events in real time, enabling PV systems to withstand extreme conditions. Nowhere is this range of capabilities more evident than in the suite of technologies we are going to hear about today. Trina is a name that will doubtless be familiar to anyone involved in the solar industry. And now the prolific module manufacturer also offers a range of cutting-edge tracker products under the TrinaTracker brand. Today we're going to learn about TrinaTracker's Vanguard 1P system, which has recently undergone significant enhancements, including increased length, a multi-motor drive system, and improved resistance to higher wind speeds, all of which will help boost efficiency and durability. We'll also explore some of the new capabilities of the updated TrinaTracker Smart solution, the brains behind the tracker, which includes the new Trina Smart Cloud, SuperTrack, and smart controllers. In short, we'll be taking a deep dive into the state of the art in tracker technology and gaining an understanding of how ongoing strategic R&D can help drive continual improvement in tracker technology and in turn support the continued rollout of solar energy around the world. So I'm delighted to welcome today three highly knowledgeable speakers who will guide us through the topic. Daniel Tobolina, Senior R&D Mechanical Engineer at TrinaTracker, Parsa Enshai, Senior Engineer at CPP Wind Engineering, and Sun Kai, Head of Tracking Technology at TrinaTracker. Together, they will walk us through some of the recent upgrades to the Vanguard 1P and the smart systems that sit behind it. As always, with our webinars, interaction with you, our audience, is really important. So please put your questions for today's speakers in the questions tab on the right-hand side of your screen. And as time allows, we will do our best to answer them in the Q&A session after the presentations. So without further ado, I would like to hand over to our first speaker of the webinar, Daniel from TrinaTracker. So Daniel, over to you. Thanks very much.
Okay, thank you, Ben, and thank you all for being here today. I'm Daniel, Senior Research and Development Mechanical Engineer at TrinaTracker. Today, I will introduce the latest updates on our Vanguard 1P and how this will enhance the tracker scenario, adding value to our customers. So first of all, let's introduce TrinaTracker and the main target of our upgraded Vanguard 1P smart tracking solution. TrinaTracker is a global company with 19 years of experience in the solar industry, which has delivered more than 9 gigawatts in more than 40 countries with a global production capability of 10 gigawatts, and a global and local supply chain with factories in China, Spain, Saudi Arabia, and Brazil. During the last 2 years, since we released the Vanguard 1P, we have delivered several Vanguard 1P projects in Asian Pacific region, China, Europe, and Latin America, with some projects over 500 megawatts, such as Santa Lucia and Uzbekistan. As always, when we are talking about TrinaTracker product, the Vanguard 1P has been certified by third parties, and here we can see some of the certifications, such as the bankability report, the UL and the IEC certifications, and the wind tunnel test. In addition to this, we always do firstly empirical tests internally in our facilities in Europe and in China in order to ensure the reliability of our products. Now we wanted to go further. We wanted to keep offering to our customers the best solutions. And this is the reason why we decided to upgrade our Vanguard 1P. As we all know, we will face different terrain challenges depending on the location of our project. But the main landform on Earth is plains, flat terrains, and the largest areas are mainly located in China, Australia, Middle East, and Latin America. And here in these large and flat terrains is where we focus on to develop our Vanguard 1P. This upgraded version is the optimal solution to large flat terrains, and it has been validated in terms of reliability under extreme weather conditions and is compatible with all the modules available in the market. We are not offering just a tracker, but a comprehensive and smart solution that integrates the SuperTrack smart algorithm that increases the energy gain and the benefits of our Trina Smart Cloud SCADA. Later on, Sunkai will get deeper when we'll give you more detail about this system's smart system control. Now let's see a video introducing the upgraded Vanguard 1P. Well, now how this upgraded Vanguard 1P will enhance the tracker performance? Well, by giving response to the need of an optimal tracker for flat, large terrains, compatible with the biggest modules available in the market, with a reliable solution which also mitigates the complex construction issues. And this is what TrinaTracker did. We increased the tracker length up to 140 meters, so now it's available for 3 strings of 210 thels modules, the biggest ones, and 4 strings of 182 thels modules. And we did it in a reliable way with multi-drive systems and a multi-damping system. Later on, I will give you more details about the importance of these systems in terms of reliability. With this new length, we are able to install 3 strings of 700 watts modules, so we are increasing the tracker capacity up to 63 kilowatts, and we are reducing the cost by 2%. So we are maximizing the generation of energy, and we are reducing the cost of your projects. In addition, this new length is also compatible with 4 strings of 182 test modules, which will demand a tracker length of 139 meters, which is a length over the conventional tracker length you will find in the market. But TrinaTracker can do it. The second point, now we have a longer tracker, we have bigger modules, how to ensure this solution is reliable. Well, as I already advanced previously with the multi-drive system. With the single drive system, the longer the tracker, the bigger the torque peak will be, so we will have less critical wind speed. But by adding a second slew-in drive, we are reducing the working span, we are reducing the tributary area of each. So now we have less torque peak and we have a more evenly torque distribution along the tracker. So we are having a better wind resistance. So we are adding an additional slew-in drive, we are making stiffer the tracker, we added an additional set of dampers, so we are improving also the damping ratio of a longer tracker. And how we prove, how we test this is actually reliable? Well, we are working together with a credible third-party wind engineering consulting company, which is CPP. And always, in all our products, we always do wind tunnel tests. We do pressure studies with the rigid tracker model, so we can get the pressure coefficient and the dynamic amplification factors. We also do free vibration tests in a full side tracker, so we could get the natural frequency and the damping ratios in torsional and heaving directions. And we also do aeroelastic studies with a flexible tracker model, so we can get a minimum critical wind speed. In addition, we are going beyond the conventional wind tunnel test configurations. And in TrinaTracker, we also test different configurations. We test under different east-west slopes, different terrain categories, and different tilt angles up to 75 degrees. By doing this, we have more information, we have more data, so we are able to offer to our customers the best solution, an optimal one, in a reliable way, so we could meet the project demands with a realistic design. By doing this wind tunnel test, we could define the optimal stow strategy, in this case 30 degrees facing the wind, and in addition we have defined 2 pre-alarms depending on the wind speed. With these pre-alarms, we will reduce the tracking angle. And by doing this, we are maximizing the energy production and we are reducing the time the tracker will take to go to stow position. So with this alarm, we are protecting the tracker, but we are also protecting the modules, now they are bigger, with the hail alarm. By triggering the alarm manually, the tracker will rotate, so the module direction will be parallel to the hail fall direction. So we are reducing the impacts and we are reducing the energy of each impact, protecting the modules. Now, last but not least, the complex construction issue. How to solve issues like complex and long construction periods and high labor costs. Well, thanks to our designs, we are reducing the installation time. With our shrink tube connection, we are saving 50% tube connection time in comparison with the conventional solutions. With our patented spherical bearing, we are absorbing irregularities of the terrains and no installation calibration is required. And finally, our multi-motor system, compared with the standard mechanical solution, we are reducing by a 34% the parts, and that means it's easier to install, faster, and we are reducing the maintenance labor. So summing up, which are the values we are adding to our customers? We are offering the optimal solution for large flat terrains with a longer tracker, up to 104 meters, which is compatible with 3 strings of the biggest modules and 4 strings of the 182 thirds modules. And that means that we are powering the energy production and we are reducing the cost of your projects. The second one is that we are offering a stable and reliable system thanks to the wind tunnel tests we do, the multi-drive systems, and the protection strategies for harsh weather conditions. And finally, the quick installation. Thanks to our designs, thanks to our components and systems, we are reducing the installation time and we are reducing the maintenance hours. Finally, I just wanted to highlight again that we are not just offering a tracker, but a comprehensive and a smart solution integrated with the TrinaTracker TCU, the Trina Smart Cloud SCADA, and our algorithm SuperTrack. So we are offering a smart digital control system too. Later on, Sunkai will give you more details about the benefits and characteristics of these systems. Thank you so much for your attention.
Thank you very much, Daniel, for that overview of the recent upgrades you've been making. Very interesting. Thank you. So we'll come on to our second presentation of the webinar. I'd like to introduce Parsa Enshai of CPP Wind Engineering, who will report on some of the testing work carried out on the Vanguard 1P. So over to you, Parsa. Thanks very much.
Thanks, Ben. Let me attempt to share my screen. I believe you can see that now. Okay. All good. Perfect. Cool. So thank you for the introductions. As Ben said, I work as a wind engineer at CPP. And here we've worked with Trina for many years on multiple projects, and we have an ongoing collaboration. So it's an absolute pleasure to be here presenting some of the services that we've worked on together. And I'll be happy to answer any questions after, or if you have any questions later on, please feel free to reach out after the webinar. So just to give an overview of who we are, CPP, or Cermaq Peterka Peterson, is a group of experts essentially mixing the art of aerodynamics and structural engineering. We have offices in the US, Australia, and other locations around the world, and 4 boundary layer wind tunnels. So 2 of those are in Colorado at our US office, 1 in Sydney, where I'm based, and 1 in Kuala Lumpur in Malaysia. Now, we don't just have experimental capabilities, we also use CFD or computational fluid dynamics to then complement our scope of services. Bread and butter and history, really, over the past 40 years or so, is a focus on the services that you have in the pictures on the right here. So these are your tall buildings, light span stadiums, or it's a cool picture of airflow, flow over the Sydney Opera House. So we use these services generally as our bread and butter, but the focus of this presentation and what I'll talk about is actually on the pictures on the left here, which are our solar services and why they're needed and what we do in them. So without further ado, solar services can really be split into 2 main categories. So you have your product testing, which is specific to a mounting structure configuration. So this can be a wind tunnel test of a tracker, a fixed tilt system, an east-west system, or any sort of unique mounting structure. And our site-specific services, which are based on a particular site, but we'll focus for the purpose of this presentation on our product testing. So that itself can then be divided into 2 main categories that I've got up here. So you've got your rigid pressure tests that essentially use a 3D printed model that's instrumented to measure pressure, and I'll cover this briefly later, and aeroelastic models that essentially move the way the structure moves to an extent. And I'll also talk about that a little bit later. This is generally a bit more specific to trackers when you get to this aeroelastic instability mechanism. But it can really be applied to any sort of structure that's dynamic. Now, the idea of this package of services is to allow a tracker designer to go all the way from the first preliminary design all the way to the end product. And this allows a company like Trina to accurately design the structure from a wind perspective so that it's safe, it's stable, it's reliable, and it's also economical, almost most importantly in the solar industry. So the last thing that any tracker designer would want is something that's under designed, because there's a risk of failure there, or anything that's over designed, because then it's too expensive for the market. So starting with a pressure test, this first part, the assumed static analysis, assumes a rigid or static structure. So when you start design, the first step is to figure out what forces or torques the wind is applying to your structure. So the outcome of this would be your pressure, your moment, or your force coefficients, as Daniel mentioned before. And now we use a set of rows of pressure models to get these coefficients, which are generally not accurately provided in wind codes and wind standards internationally. So we've done this for over, almost a decade now, and have built an extensive database for trackers in particular for different configurations, and that's different row spacings, different heights, different tilts, as well as any kind of gaps along the panels. Now, the reason I mentioned gaps is that we know gaps can amplify loads, and it's quite important to understand that effect. So this has been a part of the extensive studies that we've done with Trina, where we've looked at the effects of essentially increasing the gap size to optimize the design itself. Oops, I jumped a slide, sorry. Okay, so now going to the bottom side of this, which is your dynamic resonance effects. So at the top, you have your static coefficients covered, but these are assuming a solid structure that doesn't move, and it's essentially not dynamic. But that's really not the case when it gets to a tracker, as most of you will know. And trackers are generally built in multiple rows, which you can really simplify as flat plates that shed vortices. So this can then lead to dynamic effects, and the idea here is to analytically analyze using the pressure data to work out what level of dynamic amplification or resonance effects you will have on your structure. And a key component here to understand is the damping levels of the structure. So as again Daniel mentioned before, we've done multiple studies with Trina to look at the various damping levels of the dampers they use, of the products that they have, and on-site prototypes to see how that ranges, so that we can use it for our aeroelastic modeling, or actually the calculations for the dynamic effects. Cool. So now here's a cool video of, I'll attempt to play this at the same time. So here's a cool video of pressures measured on 5 rows of trackers in a generic rectangular array. As you can see on the top right here, the wind is coming from the bottom right-hand side of the page. And these trackers are tilted at positive 20 degrees. So there will be, in the first row at the leading edge, that will be pointing upwards. And your uplift is really the pressure that's trying to pull the panel away from the ground is really your key design wind load here. So to describe this a little bit further, and I'll play it again, you have your red zone, which is your peak uplift pressure. And as you can imagine, this would be highest in your first row, which means that you would generally build this to be the stiffest row. And then another interesting to highlight here is that as you go halfway up the track, you will end up with this, and I'll play this again, with this red zone at this edge here where you have a gap. So this is kind of linking back to that gap study that I just mentioned to you as well. Cool. So I know the focus here isn't on very complex terrain, but I just thought I would touch base on one of the key things to consider as we run out of completely flat land to build solar on. And like Daniel again said before, that's something we've extensively studied with Trina, and east-west slopes are of course going to be part of sites regardless. So different codes and standards provide guidelines on how wind speed changes over this topography. I've got a couple of pictures from the American standards here, but this is generally limited to how the wind speed itself is changing. So what's key for trackers is that they're designed quite economically in a way that the interior rows would generally have less steel, so they'll be less stiff and than the exterior rows. Now, when you go and put these trackers on a slope, your interior will no longer experience the wind as if it's an interior row. It will now lose some of that sheltering that it was benefiting from the exterior row. So it's quite important to understand what that loss of shelter, how it affects essentially the loads in the interior or even the exterior in some cases. So we've worked with Trina to test these nominal slopes over different slopes or ridges to figure out what to essentially quantify that loss of shelter that the interior rows and in some cases exterior will experience. And it's definitely something that I recommend you consider as you build rows in the future or run sites in the future. Cool. So now moving on to my favorite topic, which is torsional instability. It's really a specific issue that we talk about mainly regarding trackers. It's probably best shown through a video, so I'll play this first. And some pictures of the outcomes of when this goes too far. And this is obviously something you want to avoid as a tracker designer or an owner of a site. And we, as much as it's exciting for a wind engineer, we help you assess the risks that are associated with such a mechanism. Now, what we offer to all of our tracker clients is a screening service to start with, and it allows the importance of torsional instability to be discussed right from the start. So that provides the client then with an opinion on the potential for instability for the initial design. It helps them kind of optimize their structure from an instability perspective and get it finalized for an aeroelastic test. For someone like Trina, we've gone through multiple rounds of aeroelastic tests on different configurations of the product to really be able to characterize that instability. Now, to actually be able to quantify how stable essentially the tracker is or the configuration is, we would build an aeroelastic model. Now, an aeroelastic model is essentially being scaled for geometry. So your chord size and your spans and everything have been scaled using geometric scale, but the elasticity of the structure has also been scaled to an extent. So when you go up to a model and move it, it will essentially move like the real system would scaled. So the idea is that we model these structures as they would be in full scale, and then we blow some wind over it at different speeds. And the outcome of such a study would be, as an example, this curve on the left here, which provides your starting tilt or some initial tilt versus the wind speed at which you would experience instability at. So there are really three main outcomes that we look for when we get to a curve like this. One is the lowest speed, so that's across all tilts. When is the lowest tilt experiencing instability, and that really helps you decide what wind speed to already be in stow for. As Daniel mentioned before, this can also be used to design a step strategy so that you can stay within those safe tilts as the wind speed increases further. So once you've then identified your stow tilt, and you've found your target design wind speed for a particular site, then you can look for a stow tilt that achieves this. So this could be something like the -30 that Daniel also mentioned that Trina employs in this case. And I should also highlight that this curve is just an example, and it will change significantly depending on the different properties of the system. So that's why you would end up with a different solution for a single drive 1P system versus a multi-drive 2P system, for example. On the right here, you have some pictures of some of the tests that we've run in our Sydney office in the wind tunnel. So a couple of aeroelastic models, and I'll just play a clip of an exterior row experiencing instability. One more time. Cool. So now, what do you do to improve the stability of the system? There are two mainstream approaches. One is increasing the stiffness of the structure and/or its damping. So stiffness can be increased by using a thicker or larger torque tube. I imagine in the case of Trina, or any really tracker manufacturer, you would go to a site that has a much higher wind speed, design wind speed, and you would use a much larger torque tube compared to a site that would have lower wind speeds. Another option to stiffen your tracker is shortening the total span of the tracker. Obviously, no one likes that in the solar industry. So as you go to larger trackers, a solution here is to add multiple drives, and that's another solution that Trina has employed here. Alternatively, or additionally, increasing damping is beneficial at moderate to high tilts. So a tracker like the Vanguard 1P that plans to stow at a moderate high tilt would benefit from having dampers on the system to, one, delay the instability, or reduce the dynamic amplification that we touched on before. Now, like I said before, they're all different solutions, and in the end, there's different routes to achieve a stable system, essentially, and we recommend testing to actually quantify the stability of the system in all cases. Now, just to quickly touch base on this as I wrap up, we have a lot of back and forth with Trina, and we consistently communicate on next steps in the system, on product design updates. I've personally been to the Changzhou office in China, and we have upcoming training sessions with the technical team at different Trina offices, including the team in South America. But as you know, this is a market that's constantly evolving, and we at CPP, we need to do the same with our solar services. So we have some ongoing development with Trina, where we'll be looking at more complex aeroelastic models to better characterize their system, as well as things like advanced dynamic analysis, where we will incorporate the structural properties of the system so that the results are more accurate and specific to the design. That's all from me. Any questions? I'm happy to answer them after the presentations, or feel free to reach out later on. Thank you.
Thank you very much, Pastor. That was really interesting. Yeah, some really good stuff there. A lot to absorb. I'm sure we will come back to some of the detail of that. In fact, yes, we've had a few questions. So, yeah. But before we get to that, I'd like to introduce the last of our speakers for the webinar, Sun Kai, Head of Tracking Technology at TrinaTracker, who's going to take a closer look at some of the smart control technologies that sit behind the Vanguard 1P. So, Sun Kai, thank you very much, and over to you.
Okay. Thank you, Ben. Thank you for your introduction. Hello, everyone. I'm Sun Kai from TrinaTracker. Today, I will introduce the latest upgraded smart control system solution from TrinaTracker. Today, I will focus on the following topics, including the general introduction of TrinaTracker's smart tracking solution, the current pain points of tracker-based PV power plant, the detailed introduction of TrinaTracker control system, as well as its core values and a global project application and a case study. And finally, I will convey an assessment from a third party to show its impact and the benefits on the customer values. Let's start by looking at TrinaTracker's smart tracking solution, which consists of high reliability supporting structures and high performance and high efficiency smart control system. TrinaTrack offers Vanguard 1P, a single road tracker, and Agile 1P, a dual road tracker, as well as fixed origin, a fixed tilt supporting structure. Trina is driven by innovation, independently developed smart control system. This includes the electrical control system, TCU and NCU, ensuring the efficient and stable operation of the system. SuperTrack is a smart algorithm is to further enhance the power generation, and Trina Smart Cloud, it's a monitoring platform that can help power plants improve their operational efficiency. And next, let's explore Trina's latest generation of smart control system. Before we delve into the details, let's first understand why Trina independently developed a smart control system. Actually, the PV power plants are facing with a lot of challenges, such as instability of power supply and a battery from TCU, as well as low communication quality and stability between TCU and NCU. These have been greatly influencing the track availability and hence the system performance ratio. Moreover, in cloudy and uneven terrains at project sites, there's significant room for optimizing power generation, and conventional algorithms cannot guarantee optimal performance. Lastly, low operational efficiency of the power station and substantial manpower input pose significant challenges for power station owners. Starting from the perspective of system stability, TrinaTracker ensures the normal operation of trackers and further increases power generation and operational efficiency of power stations. Now let's further explore TrinaTracker's smart control system, which includes smart controller, track level monitoring platform Trina Smart Cloud, and the smart algorithm SuperTrack. Next, we'll go in deeply of the details of these three products. Trina Smart Controller provides various mainstream communication methods, including wireless communication. Both LoRa and Zigbee are available, and the wired communication IS-485. Multiple extreme weather protection strategies, such as strong wind and heavy snow, ensure the stable operation of the system. Trina Controller provides various power supply options, including stream-powered, self-powered, and AC-powered, to meet the different requirements for different application scenarios. The unique dual power supply design enhances system reliability by coordinating the main switch power supply with the backup battery. Next, let's have a look at Trina Smart Cloud. Last year, we have made further advancements in efficient operation and system security. Trina Smart Cloud not only allows real-time monitoring and control of track operation, displaying operational data, but also introduces new features in operations. We are so excited to implement the 3D digital map functionality. 3D digital map provides an intuitive and vivid representation of track layout and operational status, enhancing the ability of maintenance personnel to carry out their work efficiently. The mode diagnostic pre-warning function assists maintenance personnel in identifying and eliminating risks before mode failure occurs, preventing damage and power generation losses. In terms of system security and stability, Trina Smart Cloud now supports multi-role permission management. Power station owners can define access and operation permissions based on the user roles, enabling precise management for power station owners. Trina Smart Cloud supports integrating with the Active Directory system, providing various account verification solutions for solar power station owners. The must-slave redundancy feature ensures high system uptime, while data sharing incorporates wind speed zoning functioning. Trina Smart Cloud will further enhance intelligent management of data assets. What exactly is a 3D digital map look like? So here we have prepared a short video to illustrate. Okay, Trina Smart Cloud will showcase the arrangement of the trackers in 3D modeling based on their actual layout. The trackers are represented in different colors to indicate various operational status. In case of gray or yellow labeled trackers, maintenance personnel can swiftly identify and address the abnormal trackers for accurate and rapid maintenance. How does the mode diagnostic look like? So here we also have a short video to illustrate.
The use of motor diagnostic pre-warning, as well as other digital tools, provides intelligent and accurate operation and maintenance.
Okay, based on the Trina mode diagnostic algorithm, when Trina Smart Cloud detects abnormal mode current, it promptly alerts the operational and maintenance personnel. This notification serves as a reminder for the personnel to properly check and perform proper maintenance, preventing any power generation losses or further damage caused by the motor failures. SuperTrack is a smart algorithm that utilizes Trina's patented bifacial irradiance model and the mini-shading model. By leveraging these models, SuperTrack optimizes power generation in conditions of high diffuse irradiance and reduces power loss caused by shading between arrays. In particular, SuperTrack is consisted of smart tracking algorithm STA and smart backtracking algorithm SBA. STA operates efficiently based on bifacial irradiance model. It optimizes power generation in real time by utilizing meteorological data and historical weather data. Regarding SBA, SuperTrack offers two optimization methods. The first method, represented by the blue box, relies on the terrain data. SBA automatically constructs a 3D map and optimizes the rotation angle based on the terrain. In addition, a new optimization method has been introduced, represented by the gray box. This method utilizes AI technology to automatically optimize the rotation angle based on the inverter power data. SBA identifies shaded trackers through power data without requiring additional input. The addition of this new optimization method caters to a broad range of applications. After above the introduction, let's have a short summary and have a prospect of TrinaTracker smart control system. Smart controllers offer high reliability solutions of communication, power supply, and battery. SuperTrack guarantees high performance by utilizing diffuse irradiance and mitigating or avoiding rotary shading. In the near future, more detailed study and optimization will be performed to further reduce seasonal or north and south slope impacts. Trina Smart Cloud aims at high efficiency operation and maintenance for track system, and will further enhance O&M efficiency through features such as 3D digital map and track health diagnosis. TrinaTracker's smart control system has achieved a remarkable performance globally since the first launch in May 2022, accumulating sales of 4.9 gigawatts across different regions. We believe that the next generation solution can contribute to the development of power plants through AI and digital technologies, further enhancing the PV tracking system performance and efficiency. SuperTrack has been validated and demonstrated in various projects around the world. For example, in the Campina project in Spain, on typical overcast day, there was a gain of 5.55%, contributing to an overall gain of 1.16%. In the Huake project in China, on typical overcast and sunny day, the gains were 11.83% and 1.64% respectively. In the Shandong Technical Transformation project in China, on typical overcast day, there was a gain of 10.39%, resulting in an overall gain of 2.3%. To showcase the benefit and positive impact of SuperTrack on customer values, TrinaTrack invited the third-party Black & Veatch to conduct assessment and analysis. The energy gain calculated by Black and Veatch closely aligns with Trina's simulation results. This energy gain of 3.06% will lead to 2.72% reduction in LCOE, significantly improving the customer's investment rate. Okay, that's all for today's presentation, and thank you for your time.
Great stuff. Thank you, Sun-Kai. That was very interesting indeed. A good look at the brains behind the brawn, if you like. So that's all of our presentations for the webinar. We've now got about a quarter of an hour or so for questions, and we've got quite a few coming in. So I will get to as many of them as I can, but forgive me if we don't get to all of them. I guess a fairly sort of general one just to begin with, probably for Daniel to tackle first of all, and then if either Sun-Kai or Parsa have anything to add, that would be fine. So the idea of developing a longer tracker, Daniel, what was the sort of initial motivation for that decision by TrinaTracker, and how does it benefit solar modules, you know, as they're obviously getting bigger, so, you know, sort of 700 watt plus, what's the sort of key benefit there, would you say?
Okay, so at the end, TrinaTracker, it's a business unit of Trina Solar, so we deeply understood the needs of the module market. And we know that the modules are continuously increasing in terms of capacity and in terms of size. So we wanted to offer a tracker that could fit with these bigger modules available on the market. And this is why we developed a tracker up to 140 meters with a reliable solution. So by doing this, we could install the biggest modules in the market, up to 3 streams. And we are reducing the cost of the projects. And this is the main reason we decided to increase the length of the tracker, to maximize the energy production and reduce the cost.
Great. Okay, thank you very much. We've heard a lot about reliability and performance. Obviously, durability is a key thing for trackers, and you know, we've heard about wind testing and so forth, but I just wonder if you could offer some more insight into how Trina ensures that reliability and the reliability of and performance of its designs and components through empirical testing. How is that currently undertaken?
Okay, so, well, we always certify our products with third parties, but we also, as I mentioned in the presentation, we internally did a empirical test. So the validation procedure we have internally, it's quite detailed and quite severe, so we ensure that our products are reliable. And we always start with analytical calculations, finite element calculations, and once we optimize the design, once we have validated in terms of finite element calculations, we always manufacture parts to test them empirically in our own facilities. So we have test machines, a lot of equipment, so we can test the real parts under static tests, dynamic tests, durability tests. And that is what we do. So we manufacture parts and we test the parts under service load, ultimate loads, maximum loads until failure. We do durability tests. So we are completely sure we are ensuring the reliability. And this is the second step. So first of all is the calculation. Second is the empirical test in our testing machines. And then we also have in our facilities full site trackers. So once we have validated the first and second step, we assemble the parts in our trackers. So we could do all the tests we wanted. We can do durability tests. We could load the trackers. And this is the third and final step, so we ensure 100% the reliability of our parts. It's quite important to do all these static, dynamic, and durability tests in testing machines and real trackers.
Great stuff. Thank you. There's a question for you here, Parser, about stowing of panels. What is the best stow solution, and how do you sort of make decisions about that in a system?
Yeah, it's a great question, and we probably get this at every webinar. So if only whoever the highest bidder is, I'll reveal the solution. But I'm only joking. So there isn't a perfect solution. So like I said, there is a different approach and different trade-offs to consider, whether it's power generation, your wind loads, your dynamic loads, and all these considered. So there are many different solutions that will get you a stable, reliable tracker. And really the idea is to consider wind effects rather than try and find a perfect solution that everyone can then stick to. That's why you've got so many great products in the market. And yeah, there is no perfect solution, essentially.
Okay, and in terms of sort of testing that you undertake, I mean, do you need to undertake a new test for each site, or is it a sort of slightly more generic approach than that?
Yeah, sure. So generally, we would be testing for kind of open terrain where most of these trackers would be built. So for our product testing, it is tested under sort of generic conditions, or nominal conditions, I should say. That wouldn't then need to be updated for every site. Of course, there are unique sites that might have topography, and you may need unique studies for them. But generally, no, you don't need to take different tests for each site.
Okay, great, thanks. There's a few quite sort of technical questions here, which are probably best directed to Sun Kai regarding the communication methods here. So in terms of wireless communication, LoRa or ZigBee, can you talk a bit more about the communication systems in your technology, Sun Kai, and decisions that you've made around that?
Okay, no problem. Okay, so actually, for TrinaTracker, we offer 3 communication solutions to flexibly meet different requirements in different regions, because in some regions they have very strict limitations for the communication frequencies. So anyway, we offer the 3 communication solutions to cover more application scenarios, to cover more regions, to meet different requirements. And in general, I mean, from the perspective of technology features, Trina recommends LoRa for those projects with flat terrain. But anyway, I mean, if the clients requested a certain kind of communication, right now actually Trina can offer. I mean, but from Trina's perspective, we recommend LoRa for projects with flat terrain.
Okay, and a few more quite detailed technical ones here, so we'll stick with you for a bit, I think. The various power supply methods for the Trina TCU, what are those, and what are the specific low temperature solutions for each power supply method used? Okay.
So also, as I mentioned in the presentation, so right now TrinaTrack offers 3 power supply solutions, including stream powered, self powered, and AC powered, to meet different requirements from the customer end. Due to the limitation of backup battery inside, AC powered is able to work at extremely low temperature, up to -40 degrees, while stream powered and self-powered TCU can just work at -30 degrees. So I mean, it also depends on the specific conditions of the project. And for Trina, actually, we can provide the three solutions.
Okay. There's a question here about the 3D digital map you've mentioned. What the differences are between the digital map and the 3D digital map. I wonder if you could just offer some clarity on that and a bit more detail on the 3D digital map.
Okay, actually, in a previous, for the last generation Trina Smart Cloud, we offer the digital map. It's a 2D representation, and for the latest generation Trina Smart Cloud, we offer 3D. And I think it's the obvious difference lies in the display of the track layout. The 3D can provide a more visually intuitive display of the actual layout and operational status, just as I showed through the video. And this will certainly facilitate the precise and efficient fault localization during the operational phase, enhancing the O&M staff efficiency. So I think it's quite important for the for our customer, especially for their O&M. So I think that's obvious difference between the 3D and the 2D digital map.
Okay, thank you. There's another one here about the SCADA aspect of the system, and the question was, can the tracker level SCADA be synchronized or incorporated to the main SCADA of the PV plant so that all the SCADA systems are sort of in one place? So a question about linking different levels of SCADA within the system, including the tracker one.
Of course, because right now for Trina Smart Cloud, it's just a track level SCADA, and for Trina Smart Cloud, we just focus on the track level data management. Of course, for example, if the main SCADA or the plant level SCADA needs the track data, of course we can forward this data to the main SCADA through the requested protocol. Of course, right now we can do that.
Great, thanks. I've had a few questions come in which are all slightly different but also linked. So I'm going to try and to sort of wrap them into one. They concern the deployment and operation of trackers in sort of dusty, windy, dry conditions, presumably sort of desert areas, or the example given by one question was sub-Saharan Africa. I wonder, maybe Daniel to begin with, I don't know who'd be best to answer this, but I wonder if you just could offer some thoughts around the operation in these sorts of conditions. Also some thoughts around the cleaning aspect. Maybe a lot of PV systems obviously have specific cleaning technologies incorporated now as well. So any thoughts you might have on how on the one hand, trackers function in such conditions, but also how they maybe sort of dovetail with cleaning technologies as well. So some thoughts on that would be great.
Yes, for sure. So our trackers are designed to this kind of terrains, this kind of scenario. We have done this IP test in our components, and regarding the dust on the modules, we always integrate our cleaning operation mode, so the customers could trigger this operation mode. So we turn the tracker to the cleaning position, so the robots could just go through the trackers and clean the modules. So our trackers are compatible with the cleaning robots. There is no issue on that, and we can implement this cleaning operation mode. Yeah.
Great, thanks very much. Anything to add on that, Sun Kai, or does that pretty much cover it, would you say?
Actually, right now, as you mentioned, in some regions there's heavy dirt, and actually the cleaning robot has been a good partner for the PV modules as well as the trackers. So actually, I think it's quite common, in the PV plants. And but before the use of the cleaning robot, usually from the client's end, we also from the track end, we need to do a match test, several match tests to ensure the cleaning robot is matched well with the modules, with the trackers. Also, it's as for the for the stow positions, so because usually the cleaning robot will work at night. So basically, as long as the cleaning robot can determine or confirmed with with the tracker the stow angle. So I think it can be solved well. So I think it's actually right now it has been a very common practice for the PV power stations that use cleaning robots in the regions with heavy dirt.
Okay, thanks. There's one here. We haven't got a lot of time left, but I like this question. Sort of looking ahead a bit. One of the big themes, I guess, that we've been hearing more and more about over the last year or two is the integration of solar with farming, so agrivoltaics. And I think there's quite a lot of activity in that area at the moment, sort of on the technology side. The question was about whether Trina had any plans for further modifications to your technology to optimize for specifically agrivoltaics, which would probably, as the questioner says, require shorter tables, more motors, and additional tilt control beyond following the sun, presumably to customize to sort of specific agricultural activities, I would guess. But quite a nice question that. I wondered if anyone had any thoughts on that.
Okay, so I'll go first because actually about 1 or 2 years ago we have received the similar request from some regions, especially in Europe, because in Europe some some farmers, some farms or other agriculture, they want to use the PV modules, PV trackers. Of course, as you mentioned, if we want to use the trackers in the agriculture, we need to optimize the structure part. Probably for this part, Daniel can make some supplements. And I want to stress that from the perspective of, the control, how to control the trackers to balance, the PV output and also, the growth of the agriculture. It's also very important, and I think it's I cannot give a single like the algorithm, because for some plants they like to receive more irradiance, while for some plants they don't like irradiance. So I think it depends, and it depends on the specific the agriculture that will use the trackers and the PV modules. Yeah, that's my idea about.
Okay. Thank you. So no one size fits all. Then I think probably we could summarize that as being. Thank you, Daniel. Anything you wanted to add just finally on that?
Well, with regards to the structure, we have our Vanguard 2P, which has a higher ground clearance compared with the 1P products, also a higher pitch, so the machinery could go through the rows, and also we are reducing the number of piles per megawatts with this solution. So this solution, depending on the crops and the project conditions, for sure, could be used for this agrivoltaic need. Yep.
Great, thank you. Well, I think we just got time for a closing question about the sort of availability of TrinaTracker. Obviously, the PV market is booming worldwide. It's finding its way into more and more geographies. I wonder, Daniel, perhaps if you could just offer a concluding thought on, how TrinaTracker is keeping up with demand, global supply chain strategy, and how you cater to the demands of a very fast growing global industry.
Okay, so we have a global supply chain strategy, but we are developing our local supply chain strategy, and we're having factories and supply chains in different regions. Well, as I said in the presentation, in China, in Europe, in Spain, in Brazil, and this way we could give a faster response to our customers and to the dynamic solar market. And for example, with the latest opening was the Brazil factory. And thanks to this opening, we could give a faster response to our customers in Latin America and Caribbean region. And also we are aligning with the Brazil local content regulations. And the latest news is that we get the FINAME certifications, and that means that our customers could get benefits in terms of less interest and better financing options, so greater economy advantages. So we are focusing on keep growing and keep increasing our global supply chains globally and locally.
Super, thank you very much. Well, that does bring us to the end of this webinar. I know I've not quite got to everyone's questions, but we are out of time, sadly. I hope you have found what you've heard today informative and stimulating. I know I have. Recordings of the presentations and the slides you've seen will be emailed to webinar participants in the next few days. We've had a few questions coming in about that, so they will be available. And the whole webinar will also be available to download shortly from the on-demand section on PV Tech. So that's pv-tech.org. So look out for that. Will take us a little while to get it up, but it will be there. So all that remains is for me to offer a huge thanks to TrinaTracker for sponsoring this webinar, and of course to our presenters today. Their contact details will be on the presentations you receive after the webinar. So if you had a question and I didn't get a chance to ask it, then you'll be able to make direct contact with one or all of the presenters today to keep the conversation going. So thanks to everyone for tuning in today. Goodbye from me and from all the team at PV Tech. Have a great day. Thanks very much.